Can everybody hear me up there? Are we good? Okay. So last time we talked about context-free grammars, context-free languages, and push-down automata. We said that a push-down automata is simply a finite automata with a stack. So it has a stack that it can read and write from, but only at the top, pushes and pops. And so it's a restricted memory access, LIFO, last in, first out, so it's a stack. So here's the finite automata component of the PDA, of the push-down automata. Here's the stack, and you can push and pop from the top of the stack. So we said that non-determinism is built into the push-down automata. We said that a language is context-free if and only if it's accepted by some push-down automata. Which one? We don't care. As long as there's one exists that accepts it, that language is context-free. And we said that there's an equivalence between context-free grammars on one hand and push-down automata on the other hand, and it's a complete characterization. For every context-free grammar, there's a push-down automata that accepts the language that it represents, that context-free grammar represents. And conversely, for every push-down automata, there's a context-free grammar that represents the language accepted by that push-down automata. It's a complete characterization, much similar to the characterization of finite automata and regular expressions. So this is the analog equivalence here in the context of context-free language and push-down automata. So we started with a few closure properties before we left last time. So the closure property of closure under union, context-free languages are closed under union. Why is that? Because you can run non-deterministically the two push-down automata in parallel on the same input string, and if one accepts, you accept. If the other accepts, you accept also. If both accept, of course, you also accept. So as long as one of them accepts, you can accept, and so non-deterministically you can run two push-down automata in parallel on the same input, and if you do, you can accept whatever the union of the language respectively is. So any questions about that? Alternatively, you can also prove it using grammars. You can say one grammar, a new grammar, goes to the start state of both grammars of representing both context-free languages of the two machines, the two push-down automata, or simply of the two grammars, let's say. And the super grammar will bifurcate into the two start symbols of the two grammars respectively, and then you have a super grammar that's the union of both grammars, and that super grammar will accept the language that's the union of whatever the two languages accepted by these two grammars are, respectively. How many understand this proof? So we gave two different proofs, a machine-based proof and a grammar-based proof, and they're both equally valid. It's good to be able to prove things two different ways to corroborate what you think is true. Make sure you didn't make some logic error or missed some important detail. Next closure property. Context-free languages are closed under Kleene closure. So how would you prove that? So you can derive a new grammar for the Kleene closure. So if you have an old grammar, G, with some start symbol that goes to a bunch of productions, what you can do is create a new grammar, G prime, with a new start symbol, call it S prime, and S prime goes to S prime or S, or to epsilon. So this new grammar will produce as many S's as it can, or as it wants, any number of S's, by applying this rule repeatedly, right? So as many little S's will be invoked by this rule, and then finally it'll terminate with an epsilon with nothing. Meanwhile, each one of these little S's will go to whatever this start symbol S in this other grammar, this initial grammar, will go to independently of one another. In other words, it'll produce as many strings in this old grammar juxtaposed, concatenated side by side. So it's a looping mechanism over the entire original old grammar, G. How many get that? Okay. So with this simple modification to the grammar, adding this one new super rule, you can basically accept any number of strings from the original grammar's language concatenated together, which means you're accepting clean closure. Because that's what clean closure is, right? It's as many concatenated copies as you'd like from the original language independently of one another. Don't all have to be the same string when you concatenate. Each one can be a different string as long as all these strings are in the language. Any questions about that? So we just proved that the context-free languages are closed under clean closure. If you have a language that's context-free, take the clean closure of that language, that's context-free too. And we had a grammar-based proof for that. Okay. One caveat here, make sure that this new symbol S prime is different than this S. So they're not both called S, otherwise there'll be confusion. So whenever you conjoin grammars or bash them together some way or surgically splice them or group them up, or make sure that the symbols are all different from one grammar to the other. Otherwise, you might have the same problem you have in a programming language environment where you have two subroutines using global variables that clash, the same global variable inadvertently, right? Both programmers may have used employee name as their variable name for the name of the employee, inadvertently choosing, and it's a global variable perhaps, and that'll clash between two subroutines written by two different people. If you try to run them both in parallel, they may clobber each other's variables. How many get that? So you have to be careful. But it's always easy to avoid that by renaming the variables. The compiler, the computer, the operating system doesn't care what the variable names are. They're just labels to distinguish things. Okay. Keep that in mind. Okay. The context-free languages are closed under intersection with regular languages. Why is that true? Why is a context-free language intersected with a regular language necessarily context-free also? Any thoughts? Let me ask an easier question that you've seen before. Why is it that the regular languages are closed under intersection? The regular languages are closed under intersection. Try to answer that with, 2 words, not 3. What's the proof technique? Yes, you could. Is De Morgan's law 3 words or 2 words? Anyway, but yes, if you want to argue it from a machine standpoint, like a machine-based proof, what 2 words would you use? Parallel simulation, good. If you had to use a pair of different words, cross-product, construct, all similar. I mean, you're all right. You're all correct. So you're simulating both machines at the same time with a cross-product construction or parallel simulation, or you can use De Morgan's law kind of arguments. Now, back to this question. Why are context-free languages closed under intersection with regular languages? Because they're not closed under intersections with each other. That's the next theorem. Right? Context-free languages are not closed under intersection, only with intersection with regular languages, and there's your hint. Simulate the PDA and the finite automata in parallel. What does that mean? How would you do that? Not a trick question. It's straightforward now. Simulate the PDA and the finite automata in parallel. Cross-product construction will still work here. How many see that? Yeah, you're just crossing the PDA with the finite automata. The PDA needs to use the stack. The finite automata doesn't, right? Because it doesn't have a stack. It doesn't need a stack. It doesn't use a stack. So it's okay. So the simulator could be another push-down automata, and allowing the simulated push-down automata to use the simulator's push-down automata as its own stack. How many get this proof? It's a cross-product construction, basically. Right? And you accept if and only if both accept. Right? Now, why isn't it true that the context-free languages are closed under intersection? That's not true. They're not closed under intersection. Why not? Why can't you use a cross-product construction to bash together in a parallel simulation or cross-product construction 2 context-free languages? Why can't you simulate 2 PDAs? They both need a stack. And so if you only have one stack in your simulator, because you're another PDA, supposedly simulating 2 PDAs at the same time, if one of the PDAs you're simulating uses its stack to push and the other one uses its own stack to pop, you only have one stack to work with. And so what do? Do you push or do you pop? And you get conflicts on the stack, right? Is that what you're going to say? Yeah. So Now, so that's an intuition, it's a correct intuition, but it's not an absolute proof. How many get that? It's not a proof to say that I don't see how to simulate two stacks with one. That's not to say that somebody else can't see it either, or there's no clever way of getting it done anyway, right? Just because you don't see a way to do it, or it's not obvious how to do it, doesn't mean it can't be done, right? Pretty straightforward. So here's a more decisive proof. Proof by counterexample. Find two context-free languages whose intersection is not context-free. And if you can do that, you're showing the non-closure very explicitly using a counterexample. So the language 0 to the n, 1 to the n, 2 to the n is not context-free, it turns out. I think we mentioned that. Did we mention that? Yeah. Just like 0 to the n, 1 to the n is not regular, and we're about to prove that today, by the way, that 0 to the n, 1 to the n is not regular, using the pumping theorem. Okay, but this is not context-free. Not context-free. Can you guys all see that from up there? Okay. Try to gauge the angle up there. Okay. But if you take two other languages which are context-free, 0 to the n, 1 to the n, 2 star, right? Well, this is a context-free language. How many believe that? How would you recognize this with a PDA? 0 to the n, 1 to the n, 2 star. Not hard. Any thoughts? Let's get more people participating so it's not a monologue over here. Yeah. Well, but this is not the intersection of this and this. It's a concatenation of both of them, right? Well, I guess if you said concatenation, you'd be right. So it's 0 to the n, 1 to the n, which is context-free, concatenated with 2 star, which is regular, and also context-free. And context-free languages are closed under concatenation, you know. But not complementation. The concatenation, I guess, I didn't list on this slide, but they are closed under concatenation. But how would you argue simply based on a PDA? Give me a PDA that recognizes this. Give me a push-down automata that recognizes 0 to the n, 1 to the n, 2 star. Not hard to do. It's not a trick question. Nothing I ever asked is a trick question. It's all pretty straightforward. 0 to the n, 1 to the n, 2 star. You have a stack. How do you do it? Yeah. Yeah, push all the zeros to the stack. When you get to the ones, and you know because you ran out of zeros, now you're seeing a 1, pop the zeros from the stack against the ones that are in the input, 1 to 1. And then you'll know they're in equal numbers. And then when you see the 2s beginning in the input, what do you do then? What do you do with the 2s? Just flush them. Just run through it and don't do anything. Now, can you just accept right here when you see the first 2? There could be other than 2s. It could be more zeros or more 1s, and then you can't just flush those. You have to reject because that's no good. All right, so basically the heavy lifting part here is just comparing the zeros to the 1s. We're using the stack. How many see that? And the PDA can obviously do that, just like we just said. So that's context-free. Here's another language that's context-free. 0 star, 1 to the n, 2 to the n. That's context-free also. Why? Basically the same thing as the other one, except flush the zeros first, then compare the 1s to the 2s using the stack. And then you'll know. And then you can accept if and only if it's of that form. So that's context-free also. How many see that? Good. What's their intersection equal to? The intersection of these two languages. Somebody else answer. Let's get more people participating. I don't want to have to start calling on people. Don't make me do that. So participate more. Yeah. Yeah. The intersection of those is equal to this, right? This means the zeros and the ones are an equal number. Here, the ones and the twos are an equal number. So the intersection means all three must be an equal number, zeros, ones, and twos. By what property is that true? If one language preserves the constraint that the zeros are equal to the ones in number, the other language makes sure that the ones and the twos are an equal number. Transitivity of equality, yeah. How many see that? So that's kind of the fundamental principle at work here. Equality is transitive. Many operations are not transitive. Right? Okay, so we have the intersection of two context-free languages that's equal to a language that's not context-free. End of story. Right? So the context-free languages are not closed on the intersection. So we just proved this theorem. Any questions? And we proved it with a counterexample. Right there. Okay? And there's many other examples you can come up with that say the same thing. Now, does this theorem mean that whenever you have a context-free language and another context-free language, you intersect them, the result must be not context-free? How many say that's true? Cannot be context-free. How many say it may or may not be context-free? Good. Yes, my Padawans, I am proud of you. Yes, it's not necessarily the case. It could be the case, or it could not be the case, depending on what the situation is. So closure means it's always the case that it's an object of that same type as the operation involving those two things. Non-closure doesn't mean it's not that same type. It may or may not be that same type. Okay. And the homeworks have a lot of examples of these kind of questions. All right, so we just proved this theorem. Now, next theorem, the context-free languages are not closed under complementation. How would you prove that? Hint, the Morgan's law, right? What does that mean? What does that hint mean, the Morgan's law, to prove this theorem? Context-free languages are not closed under complementation. Let me not be presumptuous. What is the Morgan's law?
Well, I was going to say because the union is closed, the intersection is not closed.
So if you try to show closure under complementation and or closure under intersection, if you have two sets, let's call them L1 and L2. The languages are sets, but it's true about sets in general, right? So the intersection of two things is what in terms of the union of them? What's the set identity here that we're looking for? How do you make these two things equal? Yeah, complement L1, complement L2, and then you can complement this whole side. But instead, let's complement this whole side. Same thing, right? When you complement, when something is equal to the complement of the other thing is equal to the complement of the first thing, right? That's what complementation means. All right, and that's the Morgan's law disguised as a set identity. And the Morgan's law, strictly speaking, is about ands and ors, right? The and is the not of the or of the ands. And the or is the not of the end of the nots. Hope I try to say that three times fast. How many get that, the Morgan's law? But here we use the set identity version. This is true about arbitrary two sets, L1 and L2, or S1 and S2 if you want to call them S's. Okay, so what does this mean? This means that if complementation preserved context freeness, we know that the union preserves context freeness. How do we know that? That's the first theorem we proved, that the union preserves context freeness. So union preserves context freeness here. If complementation preserves context freeness too, and L1 and L2 are context free, by definition, right? Both of these are context free, L1 and L2. If the intersection preserved context freeness, and the intersection is equal to the complement of the union of the complements, if the complement preserved context freeness, The complement of L1 would be context-free. The complement of L2 would be context-free because it presumably preserves context-freeness. And then the union is context-free because union preserves context-freeness over here. And the complement, we presume, preserves context-freeness. And so the complement of this context-free thing under that would be context-free also. And so the whole right-hand side will be context-free. But the right-hand side is equal to the left-hand side. Because equal things have equal properties, aside from having equal values. Think about that, right? If two animals are the same animal, and one of them is a mammal, they're also both mammals. Never mind that they're both zebras also, as a side, fact. So the left-hand side will then also be preserved as a context-free language, but the left-hand side is the intersection, and we already know that intersection does not preserve context-freeness. How do we know that? Because we proved it up here. Here's the intersection of two context-free languages. The result was not context-free. So union preserved context-freeness. If intersection preserved context-freeness too, if complementation preserved context-freeness too, so must intersection, because it's equal to some function of union and or complements of things, according to the Morgan's law for sets. I use a lot of words to say that, but you can say it much more succinctly, right? You can say that if union preserves a property and complementation preserves that property also, intersection must do that as well, preserve that property. End of story. How many get that? And notice I said property, I didn't say context-freeness, because this result is true about any property at all. Regularity, decidability, recognizability, solvability in non-deterministic polynomial time, whatever. Any class of languages that has a certain property that's preserved under union and complement, that property must also be preserved under intersection. And if it's not preserved under intersection, let's say you have some property of languages, some arbitrary class of languages. I'm not even saying which, just arbitrary class of languages. And you know that intersection doesn't preserve a certain property. What can you tell me about preservation of that property under union or intersection? What can you say in general now? If I'm telling you intersection is preserved, the intersection preserves the property, what can you say about union or complement? Yeah. So if intersection is preserved, let me ask it a different way. Let's say if the intersection is not preserved, let's put it that way. If the intersection is not preserved, what else can you deduce from that? Yeah, the other two cannot both be preserved. Either you lose the union preservation property, or that property is not preserved under complementation. One of those two, or both. Both may not be preserved. Right? But at least one of them it's got to go. You can't have both of them be preserved, because the intersection could be expressed as equal to some function of these other two properties, union and complementation. So one of those two cannot be preserved if the intersection isn't. And you can write this the other way around. If you put the complements over here, you could write this like this. You can say L1 intersect L2 is equal to, and here we'll say L1 and L2 union, and then we'll put the complements over here. I can do that, right? How many buy that? Okay. So that means if the union is not preserved, then one of the intersection or the complement can't be preserved either. So it works in both directions in some sense. So of these three properties, if one is preserved, if one is not preserved, one of the other two can't be preserved either. So that's general. So any questions about that? So we proved this theorem here, not just for context-free languages, but for any property, any class of languages. Yeah.
Would you say that if every operation in an expression preserves a property, then you can automatically assume that entire expression preserves that
Yeah. So he's saying if every operation involving an expression, like something is equal to, the complements and unions and intersections and even concatenations or Kleene closures thrown in, you have this long, big expression here on the right, and each and every one of these operators preserve some property, then the entire expression, whatever that is, preserves that property too. How many believe that? Yeah, because it's preserved through every stage of manipulation of that expression. Every time you hit it with another operator, you get preservation of that property. So for example, if addition preserves integerness, in other words, every two integers added together is another integer. It's not a irrational number or a complex number or a matrix out of the blue, right? So if addition preserves integerness, and so does subtraction, and so does multiplication, any arithmetic expression involving addition, subtraction, multiplication, or even exponentiation will preserve integerness too, right? You don't even have to start from scratch, except except for 0 to the 0 or something that might not be undefined. You have to worry about that case, but really that's what it is. Yeah.
So would you have to restrict that to finite number of operations because you start talking about?
Yeah, that's a good point. So it's a finite number of operations. So when you said an expression, I took it to mean quote expression unquote, which means it's a finite expression. It's not an infinite expression. If you start adding together 1 plus 1 plus 1 plus 1 plus 1 all the way out to infinity, the answer is not an integer. How many get that? So an infinite number of applications of an operator doesn't necessarily preserve the property that 1 or 2 or 17 applications do of that same operator. Strange things happen at infinity. You already know that from doing homework number 1, right? Any other thoughts or questions so far? Yeah. Sure. Yeah, if you complement, sometimes you'll get a context-free language, but otherwise, sometimes you won't. Give me an example of a language that's context-free whose complement is also context-free. Excellent question. So I'm turning it to the class. He's asking for basically an example of a language that's context-free, such that when you complement it, it's still context-free. So in this case, complementation did preserve, but it was a fluke. So give me a fluky example where complementation preserves context-freeness. Mm-hmm.
So if we hit a 0, we go to the except state, we loop around there, otherwise we loop around to the other place. And then we've got the other language, that's every language without a 0 in it. So if we hit a 0, we go to return
okay.
state, loop around there, otherwise
Language of all strings with zeros and strings without zeros. Give me an even simpler example. Correct, but give me an even simpler one.
empty language versus a language that accepts.
Yeah, the empty language is context-free. The complement is what? Sigma star, it's everything. That's also context-free. In fact, both are regular, not just context-free. And incidentally, everything that's regular is also context-free. Prove that separately. Why is a regular language necessarily context-free? We already mentioned that, but that was maybe 2 lectures ago, so let's mention it again. Yeah, PDA can simulate a finite automata. Just don't use your stack and your finite automata. So don't use that superpower, right? Superman can easily simulate Clark Kent, right? But an average human cannot easily simulate Superman, not when push comes to shove, right? Okay, so any other questions? All right. So here are some decidable properties of context-free languages and PDAs. Remember, we did this exercise too for finite automata. Is the language of a machine empty? We can tell that. Is the language finite? Is the language infinite? Right? Is this particular string an element of that language? By the way, that last question here, whether a string is in the language of a PDA or whether that string is in the language of a grammar, so you can ask these questions about either PDAs or grammars. What's that last question called? It has a name, it's a famous problem. I give you a string and a grammar, ask you, is that string an element of the language generated by that grammar? Give me a one-word description of this problem. Parsing. How many see parsing? Yeah. So you've all done this. You've all asked these questions and got it answered many times. When do you answer it? When you ask this question and get it answered many times a week, even many times a day as computer scientists? When you compile code. When you compile code, the compiler answers this question for you. What is this string W when you compile code, when you debug code, when you program? What is the string W called? Yeah, but even more general. Let me ask you the other question. What's the grammar in this context of programming or compiling or parsing? What is the grammar which grammar are we talking about, really? Where is this grammar? What is this grammar? It'll be the programming language's lexicographic definition of how well-formed statements and expressions are formed in this language. What's legal and what's not legal to say in this language. Right? Arithmetic expressions, if then else, while loops, array declarations, whatever it is. That's the grammar. W is what? Not hard, but your source code. Your program is W. How many get that? And the compiler answers this question. In other words, is your source code W generatable from this valid set of rules that are the grammar, that are the syntax of the programming languages? The grammar is the syntax of your programming language. Any questions about that? So I just wanted to anchor that into reality, not just reality, but stuff that you've done thousands of times already, i.e. compiled code. Right? Sometimes you compile a piece of code 50 times in 1 hour. Right? You just tweak things, compile, tweak, and try to fix all the errors. And when the compiler says it's not in the language of this grammar, that's a syntax error. Okay? And then you have to fix it so that it becomes a string in the language of the grammar, i.e. a member of the set of all valid programs. And these are your strings of the language. You see how it ties directly to programming, to compiling, to debugging, to syntax of programming languages. In fact, that's why we invented this whole theory back in the 50s and 60s, Chomsky and others, to help us write codes. And not just that, but to also help us parse natural language, understand linguistics and speech. And because when we talk, just like we're talking now, back and forth, these are also languages, except the languages are natural languages, i.e. English, Chinese, Spanish, French, and so on. But a language is a language is a language. So this theory is about any languages, not just some abstract language, but it applies to English and Chinese and French, and also to Fortran and C and C++ and Java and Python and computer languages, and to many other things. This is very general stuff. It underlies everything else. Okay, so for extra credit, try to prove some of these. Not that hard to do, but I don't want to spend precious class time on this. I want to go through a few other things. And then some properties of context-free grammars and context-free languages are not decidable. There's no algorithms for them. For the ones we saw on the previous slide, these ones, all 8 of these questions, there's algorithms for. And for extra credit, try to come up with some. Here are some questions that there's no algorithms for at all. These are undecidable, like the halting problem. If I ask you, is the push-down automata the smallest it can be? Is it minimal? Or is there a smaller one with less states that can do the same thing exactly what the other one does? Undecidable, turns out. For finite automata, it's decidable. We can minimize a finite automata. How many remember that? For PDAs, you cannot generally minimize it. It's undecidable. Whether I give you 2 PDAs, 2 push-down automata, and I say, is this the same as that? In other words, do they accomplish the same thing? Do they accept the same language? Undecidable. There's no general algorithm to determine that, and we can prove it. Is the context-free grammar minimal? Is it ambiguous? Is the 2 languages of the 2 grammars the same language? Is the intersection of the languages of 2 grammars empty or not? Is the language ambiguous or inherently ambiguous? Undecidable. So many things lose algorithmic decidability at this level of the hierarchy, of the Chomsky hierarchy. Remember, the Chomsky hierarchy is a bunch of sets of languages, classes, the regular, then the context-free, then the context-sensitive, the decidable. How many remember that Venn diagram that we keep? It's on the class website. It's so important. So as we go up this hierarchy, even at the second level of context-free, right above regular, all these properties become undecidable. At the regular languages, they're all decidable. And we already came up with algorithms for some of them 2 or 3 lectures ago, whenever it was. Okay, so for extra credit, try to prove some of these things. Again, I'm not going to spend a lot of class time on each and every one of these things, but if you want to do a deeper dive, into some of these properties and prove undecidability. Usually it's reduction from the halting problem. Feel free, and I encourage you to do that. Let's talk about enhancements to PDAs. If a PDA can have two-way capability, you can go left or right on the input based on whatever state change you want. You have the ability to go the other direction. Does this have more power than just going one direction on the input? How many say, yeah, you can do more, you recognize? Yeah, you can. For finite automata, that wasn't true. For PDA, it is. Give me an example where this gives you more power. Yeah.
You can do both you can do that.
Yeah, you can do that right here. You can recognize 0 to the n, 1 to the n, 2 to the n using a two-way. Why? Because first compare the zeros to the ones using the stack, and then that ends you up here between the ones and the twos. Then go backwards to the beginning of the ones, and then go again, flush the stack, and then go again, and this time compare the ones to the twos, and by transitivity, there'll be an equal number, and that's not context-free, but we just recognize it using a two-way PDA. And that proves this first theorem on this slide. Two-way PDAs have more power. They have a superpower over regular PDAs. Yeah?
Are two-way single-stack PDAs different in power from a one-way, or what I say, are two-stack one-way PDAs different from one-stack two-way PDAs in power?
You mean, is a one-stack two-way PDA different than a one-way two-stack PDA? Yes. But I won't try to say that 3 times fast. Basically, a two-way PDA, one stack, can recognize things that a one-way PDA can't, like this one right here, for example, and many other things, but not everything. A two-stack single-way PDA is equivalent to a Turing machine, actually. So I can do absolutely everything that's doable by a Turing machine, which is really everything that we know how to do. So yeah, that's the ultimate power, ultimate superpower. 2 stacks is equivalent to a tape, basically. And the way to prove that is relatively easy, actually. Think about the 2 stacks. Everything you take off this stack, you push onto the other and vice versa. So it's like a slinky. How many realize the slinky construction is sort of what you can do with 2 stacks to preserve everything that's on both stacks? Meanwhile, it cycles through your finite control, and you can basically use those 2 stacks as a single tape. Everything to your left on the tape is on one stack, everything to your right is on the other. And when you move on the tape back and forth, you're doing this slinky back and forth, shuffling between one stack and the other. And that's how you simulate a tape with 2 stacks. So it's a Turing machine, yeah.
But isn't the two-way of the single-stack PDA also giving you tape capability?
No, because you're going back and forth on the input, not on the stack. The stack is still access restricted. That's right. So you have the two-way capability as a read-only, not a read-write like you can with the other one, other scenario. It's a very good question. It's a subtle point. There was another question down here. Yeah.
So my question here is, if that language is not context-free, it's not recognized by a one-way PDA, the test for a two-way PDA that defines it as context-free or not, does that not matter?
Well, so a two-way PDA doesn't define context-free. A one-way PDA with a single stack is the definition of context-freeness. Now, if you start piling on superpowers and extra capability, it's no longer context-free. These are modifications to PDAs. Remember, a PDA with a tape is a Turing machine, and that can do a lot more, but it's no longer a PDA, and it's no longer defining context-freeness. It's something bigger than that. So now we're showing where the limits are of PDA enhancements, in other words, so-called enhancements. Because some of the enhancements will be more powerful, others won't. Right? So we just found an example of a non-context-free language accepted by a two-way PDA, namely 0 to the n, 1 to the n, 2 to the n right there. Second theorem, if you have 2 stacks, it's more powerful than a 1 stack, and you can basically simulate a Turing machine. In fact, this thing can be simulated with 2 stacks, plain and simple. How would you accept this with a one-way of machine that has 2 stacks?
Pop a 0 onto the stack, onto both stacks, and then pop a 1 off of the first stack.
Yeah, or you can basically push the zeros onto one stack, push the ones onto the second stack, and then when the 2s come rolling in, just pop the 1s and zeros from both stacks against the 2's incoming in the input, and then you'll know they're equal numbers. So with 2 stacks, this is very straightforward to implement, to recognize, even though it's not context-free. And in general, 2 stacks is equivalent to a Turing tape, and so it's even more than that. Yeah.
Also, just to clarify, like a context-free language is one that can be represented by a one-stack, one-way PDA?
Yes. So to repeat what he said, a context-free language is one that's recognized by a one-stack, one-way PDA. And it could be non-deterministic, too. In fact, non-determinism is built into the definition. So I don't even have to say that, but I'm saying that explicitly anyway, that non-determinism is available there at your option. Question?
So these enhancements are illustrating what the limitations are of the stock definition of PDA.
Yes.
That it's built on.
Yeah. Remember, we did the same exercise for finite automata. How many remember that? Really? Only 10 of you? Okay. Let's go back in time. It's a little hard to say. Okay. So regular expressions. Okay, here are some decidable properties of finite automata, right? Whether it's infinite, zero, empty, or 2 languages to finite automata are the same language or not. And where did we do this? Maybe earlier? Okay, here we have J-flap. Talk about non-determinism, power set construction, right? I think we did this. I'm not imagining this, right? Yeah. Anyway, I'm pretty sure we did this, right? I don't know why I can't find this right now. Yeah, so if a finite automata has 2 heads, it can recognize 0 to the n, 1 to the n, for example, right? But other things don't change the power, finite automata. And same thing for PDAs. Certain things change the power, otherwise don't change the power. Okay, so let's continue with this discussion of these enhancements or so-called superpowers. So we said that a 2-stack PDA is more powerful to recognize 0 to the n, 1 to the n, 2 to the n. If you have a queue instead of a stack, if you have a queue, you can recognize more, right, than a stack. In fact, a queue is equivalent to a Turing tape, right? With a queue, you can recognize this, right? Push the zeros to the queue, and then pop the zeros against the ones off the queue, but then while you're doing this, push the zeros to the queue while you're doing this, because on a queue, you can push on the other side than you're popping from, right? The stack, you push and pop at the same end. A queue, you can pop from one side and push on the other, because it's a line, it's a queue, right? So as you pop off the queue to the zeros to measure against the ones, to compare against the number of ones, as you pop them, keep pushing them on the other side, and then by the time you're done, you compared all the ones to the zeros in equal numbers, but now the zeros are still on the queue, and there's n of them on the queue, and now you can use that queue again to compare them against the 2's. How many get that? Straightforward, right? And in general, a queue is as powerful as a Turing tape, just like 2 stacks are, right? Because you can push and pop without losing what you're looking at. You can pop and pop and pop, and push it on the other end and still have it available, so you're cycling the queue every time. Somewhere in the problem sets, I don't know if it's on the homework or not, but somewhere in the problem sets, there's a question that asks that. And now you have a huge hint, in fact, pretty much the solution of how to use a queue to simulate an arbitrary Turing machine. And you can do more with a queue. So we just showed an example of a non-context-free language, namely 0 to the n, 1 to the n, 2 to the n, that can be accepted by a 1Q PDA that cannot be accepted by a 1-stack PDA. Okay, if you have 2 heads, PDAs are more powerful. Because if you have 2 heads, still 1 stack, take 1 head, keep it here, put the other head here, pass the 1s, pass the 0s at the beginning of the 1s, and then in lockstep, check the 0s against the 1s with the 2 heads, and then the first head will be at the beginning of the 1s, the second head will be at the beginning of the 2s, and then check the 1s against the 2s, make sure they're an equal number, and you're good. Any questions about that? So 2 heads are better than 1 is what we just proved. Right? You've heard the expression, now you know why. Yeah?
What about 2-head PDAs and 2-way PDAs? Are those the same power?
No. So, but it's tricky to see what's going on. So he's asking if 2 heads are better than a 2-way capability. Is one, because both are more, than normal PDAs. So how do they compare to each other? Is one more than the other? They could be incomparable, actually. So it's like saying, who will win in a fight? I don't know, Batman or Green Arrow? It's hard to say. Each one can do stuff that the other one can't, right? Or Superman and Flash, who would win? I mean, it depends. I don't know. So that's the kind of questions he's asking. It's hard to say, right? They're both superpowered, but is one more superpowered than the other strictly under all situations or not, right? In the most recent Batman versus Superman movie, Batman beat Superman, right? But, he had some help with kryptonite and some conniving and blah, blah, blah. And so it's generally difficult to answer these questions unless it's obvious. But people have been asking and answering lots of these questions over the decades. What about non-determinism? Does that increase the power of PDAs? Short answer is yes. First of all, it's built into the definition of a PDA. But if it wasn't, a language like WWR, palindromes, where the center of the palindrome is not marked with a $, those are context-free, but not deterministic context-free. So you can have examples of that. So that's some of the enhancements. And I'm saying extra credit, but we really answered most of them right here, at least, answered them enough so that you can kind of write down the rest of the details yourself. Yeah.
So you can simulate a queue using 2 stacks. So is a 2-stack PDA as powerful as a 1Q PDA?
Yes. You can simulate 2 stacks with a queue, and you can simulate a queue with 2 stacks. So to show that two are equivalent, each one has to be able to simulate the other. So that's one way to answer that question is you show that the one model can simulate the other, and the other model can simulate the first. In other words, show that Flash can do everything Superman can do, and Superman can do everything Flash can do, and then they're equivalent in terms of superpowers. All right, so that brings us to non-regular languages in terms of the pumping lemma. So we kept saying that the language 0 to the n, 1 to the n, the language 0 to the n, 1 to the n is not regular. We kept saying that. Let's prove it once and for all. Okay. So we prove it using the pumping lemma, or pumping theorem, and here's what it looks like. But let's explain it more intuitively. So every regular language has this so-called pumping property. Here's what it means. Let's say you're a finite automata chugging along, recognizing strings, and in comes in a very long string. By very long, I mean longer than the number of states you have. So you see a character and you jump to a state. You see a character, you jump to another state. You see another character, you jump to another state. You see another character in input, you go to yet one more state. And you keep cycling around states, and you jump to one more state and one more state as you see more and more characters. If you have enough characters coming at you, eventually what must happen to you in terms of which states you visit? You must visit the same state twice. How many understand that? What is that called, that general phenomena? It has a name. The pigeonhole principle. If you have more pigeons than holes, no matter how they bunk up into holes, 2 of them will have to be in one hole, or more than 2, but at least 2 will occupy a single hole, guaranteed. If you have more objects and containers, one container at the end will contain at least 2 objects, not 1 but 2. So number of states is finite. That's why it's called a finite automata. It's a fixed number. The number of characters in a string is not finite. Well, it's finite every string, but it's not bounded by any number. Right? Sigma star has arbitrarily long strings. That's strings of size 1,000,000, 1,000,000,000, a trillion, a Googleplex, and so on. So if you have a single finite automata that's fixed and trying to recognize a lot of big strings, eventually will come along a string that's bigger than it, has more characters in a string than states in a finite automata, and it must cycle while it's recognizing that string. So while it's recognizing that string, it's cycled among a bunch of states. And when it did that, it recognized some substring along that cycle. So it recognized some substring, right? So it started here at the initial state. It went to some state which then cycled, and that's called this string u, the string u that caused it to get from the start state to this state, the string v that caused it to cycle around, and there could be many other states here. I'm just kind of drawing it conceptually, but there's a substring u, so w is made of 3 parts, u, v. I want to make sure I use the same letters, u, v, the input, u, v, and w. Okay, so the input is u, v, w. U caused it to get to some state which then cycled, which then caused it to get to some final state, and this piece here, we call it w. So I'm consistent with the letters I'm using in this slide here, as far as the drawing here. So once this string v caused it to cycle, if along came, and by the way, it accepted this. How do we know? Because it started from a start state, went here, cycled, then went there, ended up in a final state, and accepted it, right? So once this string got accepted, what can you tell me about the string u v squared w? So this string was in the language of the finite automata. What about if a string u v squared w came along, u v v w? What will this machine do? It must also accept. How many see that? Why? Why will it also accept if u v v w came along? It's just going to cycle one more time. It's deterministic. It's bound to do the second time the same thing it did the first time. It's like Groundhog Day, with Bill Murray. How many have seen that movie? Same thing happens over and over and over again. It can't be helped, right? In fact, every u v to the I will also be an L for any number of v's, not just 2. How about 0 v's? Will uw be in the language? How many say yes? Yeah, why? Because you don't have to pass go, you don't have to collect $200, you can just go directly, without going through the cycle, to the final state, right? So this property must be true of any regular language. And what is this property? Is that if you have a long enough string, there's some piece of the string, and we're calling it v here, you can call it whatever you like, call it Joe if you like, but there's a piece of string there in this larger string that can be pumped up arbitrarily a number of times and keep you in the language, not exit the language. So every long enough string in a regular language gives rise to an infinite family of even longer strings. And they're all in the language necessarily. How many get that? Okay. So we just proved a very fundamental property of regular language. It's called the pumping property, and this is called the pumping theorem. Okay. So if you have a regular language, every long enough string in it must have a pump. It has no choice. So now look at strings of the form 0 to the n, 1 to the n. If you look at a string of a bunch of zeros and a bunch of ones, right? So these are strings of the form 0 to the n, 1 to the n, and this is an example. Ask yourself, where is this pump v, right? That must be there. Is it only across the zeros? Is this a V? If it's only across the zeros, why can't that be the case? What's wrong with that picture? If V is across the zeros, and we know V must be there, every long enough string must have a pump. What's wrong with that picture if V is, say, in the zeros? We can't have arbitrary powers of V because then you'll have more zeros than ones. If V was only in the zeros and you pump that up, it'll be out of step with the number of ones which don't get pumped. So V cannot exist in the zeros. Well, can it exist only in the ones somewhere? How many say it can? How many say it cannot? Good, for the same reason. Right? Okay, the only other choice is if V somehow crosses the zeros and the ones boundary. That's the only other general place it can be in, if it crosses that boundary. What's wrong with that picture? If V crosses the zeros and the ones boundary. Yeah, if you pump that up, if you pump this V up, the zeros and the ones will be out of whack. They'll be out of order, right? So it can't be in the ones, it can't be in the zeros, and it can't cross the ones and the zeros. Namely, it can't be anywhere in this string. There is no pump in such long strings, zeros and ones, in equal numbers. So it's not a regular language. End of proof. So we just proved that 0 to the n, 1 to the n is not a regular language. Because a regular language, if the string is long enough, it must have a pump in every string that's long enough. By long enough, mean more than the number of states in the machine that supposedly accepts that language. So if you say 0 to the n is 1 to the n is regular, then okay, then I'll ask you, okay, what's your finite automata that accepts it? How many states does it have? 10, a million, a billion, a trillion, a Google? You tell me. Even if you say it has a Google states, it's really complicated. I say fine, without even knowing exactly what it is, just knowing that it has a Google states, I'll say, okay, then the string 0 to the Google, 1 to the Google must be in your language, because all strings of that form are in the language. And you'll say, of course, yes, because you claim that your machine does it with the Google states. And I'll say, okay, such a string must have a pump. And you'll say, okay, I guess it does. I'll say, okay, fine, then where is the pump in that string? Is it only in the zeros, only in the ones, or crosses the boundary? And each one of these cases will be refuted. And so there is no pump. So then you'll look kind of quizzical at me. And I'll say, and therefore your language can't be regular, and your finite automata can't exist. And you'll be, yeah, I guess you're right. And so it's an adversarial argument. How many get this argument? Okay, it's a very powerful argument. It's a non-existence argument. We just proved that there's no finite automata in the universe that can recognize this language, 0 to the n, 1 to the n, even with a trillion states or a Google states. Can't happen. So we proved we're not millionaires. Right? That's hard to do. You can't prove you're not a millionaire by not showing me the money. You can prove you are a millionaire by showing me the money, and then I'll believe it. But you cannot prove you're not a millionaire by not showing me the money. Maybe you're hiding it somewhere in some offshore account. Maybe you have a winning lottery ticket that even you don't know about. Who knows? Right? So, but we just proved that no finite automata in the universe, and there's an infinite number of them, can do this job of recognizing strings of form 0 to the n, 1 to the n. Very powerful argument. Any questions about this so far? Now, what I just told you in the last 10 minutes is written here in logic. This says that there exists a number, a natural number, such as for all strings z in the language longer than that number, there exists a u and a v and a w that together make up that string, such that the middle part, v, which is a non-trivial part, it's not epsilon, can be pumped up to any number of powers and still be in the language for any exponent on that v. That's what this says. How many see the logic versus what we just said in 10 minutes, that one long line of symbolic logic? It's kind of a mouthful here, or more an eyeful rather. But look, the existential and universal quantifiers are nested 4 deep. There exists something such that for all something else, there exists yet something else such that for all something else, something is true. So there exists for all, they're nested 4 deep. It's a little tricky to wrap your mind around so many nestings of universal and existential quantifier alternations, but All this says is what we just said the last 10 minutes. That when you ever find an automata that supposedly recognizes the string, it's long enough, it must cycle. Pigeonhole principle, right? If it cycles, take that cycle, and you can pump it either up or down, and you must still be in the language. And that's what this says. Question?
In that logic mess there, on the right side, first line, where the Z equals UVW, shouldn't the V have an I multiplier in it?
Well, so Z, all we're doing here is breaking up the string Z into 3 parts so we can call them something. So all this says is, the first part of Z will call it U, the second part of Z will call it V, the third part will call it W, and then we can refer to the 3.
Well, right. The important part here is that V is the part that's repeated, right?
Yes.
So then you should say that there could be any number of repeats in there, because your next statement, the length of U and V must be less than N, is presumably the part where you say that U and V together, just one of those repetitions, should be shorter than the number of states in the finite compound, right?
Yeah. So what I'm saying is that the length of U and V together doesn't have to exceed N. Because as long as we're equal to N, something must have cycled. Or maybe, if you speak...
Right, but since the Z could be one of those big long strings with 20 repetitions in it,
Yes.
in order for that Z equals UVW to work out, that V, in order for the Z equals UVW and the next statement UV less than N to both work out, that V cannot refer to the entire bunch of repetitions. It has to only refer to one repetition, right?
Okay, so there could be many pumps. I'm just focusing on one, and I'm calling it V. There could be lots of other pumps there, too. Lots of pumps, yeah. But there has to be at least one of them, and it has to occur...
But V has to refer specifically to one of those pumps, right?
Yes.
So then,
But look at this symbol here in red. There exists a U and a V and a W such that V will be the pump.
right.
But I'm not saying that any partition into U, V, and W will form a pump at V. That's not what I'm saying. It's not even true.
But the string Z could already have multiple pumps in it, right?
Sure. And if it has multiple pumps, it also has one pump. If you have 7 books, you also have a book, right?
So you're saying that W has some V's in it?
It has pumps in it, but this pump, I'm calling it V. The pumps in W may be called V prime, V double prime, X's and Y's. So if you have 7 books, if that's true, it's also true that you have a book. How many agree with that? So if there's many pumps in Z, it's also true that it has a pump, and I'm calling that pump V. I'm just naming it so I can refer to it. I'm not saying it's the only pump. I'm not saying that W doesn't have pumps in it. In fact, it could. I'm not saying if W has pumps in it, they're not equal to V. They may or may not be equal to V. And usually they won't be equal to V. There'll be other pumps other than V. A pump is a cycle in a finite automata. It can be many cycles. Finite automata is a graph, right? The nodes are edges and the transitions are, the nodes are states and transitions are edges. So it can be many cycles in a graph. I'm isolating one cycle, and I'm calling it V. And then I'm reasoning about that cycle that I choose to isolate and name. There could be many other cycles, different or not different than V. I'm not concerned with those. Just like the other 6 books that you have, I don't touch them. I'm not naming them, I'm not talking about them. I'm just saying you have a book, and if that book is Paul Has How to Solve It, then we can talk about that book, and so on and so on. By the way, the book Paul Has How to Solve It, it's part of the 3rd assignment. How many have seen that already? Good. If you haven't even opened the 3rd assignment yet, I'm not sure why you didn't. It's already available. If you don't open it at all, I'm not saying you should work on it right now, every day, all day, but if you don't open it and look at all the problems, your brain doesn't have a chance to work in background, slowly simmering over these problems and potential solutions, and you're depriving your brain of doing free work for you in background. You're leaving all that equity on the table. I don't know why you do that, but that's what you're doing. So for the 3rd homework assignment, you got to read the book Polya, How to Solve It. How many have read it already, by the way? Good. The rest of you will do this by the end of the third assignment. Okay, it's a short book. It's only a couple hundred pages, and it's easy reading, and it's not dense, and it's very good advice on problem solving. Okay, so we're saying there exists a pump, V, and then for that pump we can pump it up, and it's got to occur somewhere in the first prefix of that long string. That prefix should be at least as long as the number of states in the machine. Could be even shorter, but it's not longer than that, right? That's what this is saying. Now let me ask you a different question. A language is not regular. Does this say it does not have the pumping property? We saw plenty of languages that are not regular, right? 0 to the n, 1 to the n, 2 to the n, the halting problem, lots of, WW, lots of languages we've already seen were not regular. Does that mean non-regular languages do not have the pumping property? How many say that's true? How many say non-regular languages could also have the pumping property? Okay. Are you just saying it from the way I asked the questions, or do you actually can prove that? Yeah.
We can just add a pump to the front of a non-regular language.
Yeah. Take a non-regular language, add sigma star $, that language L. And now arbitrary things are pumpable. Because all of sigma star precedes all the other strings in the language with a $sign demarcation, so it's very clear what's going on. And you just added infinite number of all possible pumps to the language. How many get that? So you can do that. You take the halting problem, add a sigma star $sign H for the halting problem language describing all Turing machines that halt on particular strings, and you just made it pumpable. Maybe it was even pumpable before, but now for sure it is. So pumping must exist in a regular language. Pumping does not have to not exist in a non-regular language, just so you know. Any questions about that? It's a necessary but not sufficient condition for regularity. Okay, another question. So here we're saying that every long enough string has a pump that can be pumped up, and all these strings must still be in the language. Does it also mean that every long enough string was obtained from some shorter string using pumping? How many say it does say that? How many say it doesn't say that? Okay. Good. It doesn't say that. Why? Well, for one thing, it's not true. So it can't say that because it's not even true. Question?
To your question on
Yeah.
Why it's unnecessary. We never said anything about the construction of that long string. We just said that if it's regular, that there's going to be, that we're going to be able to find that pump. It doesn't necessarily mean that we had to use that pump to generate that long string.
Yeah. So another way to understand that one doesn't imply the other. The fact that there's a long enough string that can be pumped up doesn't mean that arbitrarily long strings were derived from smaller pumps. Another way to explain why this is the case, imagine integers. So integers can be factored into primes, right? How many realize this? Integer can be factored into primes, right? The fundamental theorem of arithmetic. You take an integer, factor into primes, take one of the primes and pump it up. By pumping it up, we mean exponentiate it to arbitrary powers, integer powers. The result will still be an integer. How many believe that? Sure. Take one of the factors, pump it up, and you'll still have an integer that's even larger than the original. But that doesn't mean that every large integer was obtained in this way by pumping up into higher and higher exponents some smaller factors of a smaller integer. How many believe that? Prove that to me.
We could use a big
Prime
prime number.
numbers. Yeah? A number that's prime was not obtained by exponentiating smaller factors. In fact, it doesn't have any factors. Never mind large numbers of factors exponentiated. So what we're saying here is the language can contain strings that are very, very long that were not pumped up from smaller strings. These are prime strings. Strings that have no factors in it. No exponentiated factors, or at least no bigger than 3. In fact, there are strings that are cube-free. There's no substring in them repeated 3 times of any length. So there are cube-free strings. Cube means concatenated 3 times, like W cubed, W. So there's some strings in there, but such as there's no substring that was repeated 3 times in a row, of any length including 1. You can prove that, actually. It's not easy to prove, but once you see that, that means these are like prime strings. Prime with respect to concatenation and exponentiation, just like with the prime numbers example with respect to multiplication and arithmetic exponentiation. String exponentiation means concatenation, repeated concatenation. So that's what it doesn't mean. Okay, so I'm just kind of trying to help you not fall into potential traps here when you use pumping arguments. Realize what the argument buys you and what it doesn't buy you, what it does and what it doesn't do for you. It allows you to identify languages which are not regular by looking for a pump and not finding it. Okay. But if a language has a pump, it doesn't mean it's regular. And long enough strings may not have, in general, may not have a pumpable substring that got them there to be that long. There could be prime strings. So a regular language has plenty of prime strings. That's not in contradiction for one another. So sigma star is the set of all strings. How many say sigma star is regular? Yeah, of course. There's a one-state finite automata that recognizes sigma star. It just says accept and flushes everything. That's all it does. Easy to accept, easy to recognize, sigma star. But sigma star has very long unpumped strings. It has very long prime strings, cube-free strings. In fact, sigma star has Shakespeare's Hamlet in it too, and any other book or movie that you can name. In fact, any other book and movie that you can't even name because it hasn't been written or produced yet. Those are all there too. They're there right now in sigma star. Very esoteric strings. So Shakespeare's Hamlet doesn't have a pumpable piece in it, but other strings do. Right? Any other questions about pumping? So we kept saying that 0 to the n and 1 to the n is not regular, and we used that in the homework and discussion to prove things and to say now you know why it's not regular, or at least one major reason why it's not regular. It doesn't have a pump, and it should. Every regular language, for every string long enough, that string must contain a pump, and these strings don't. Okay, any other questions so far? This is a bit subtle. The proof by contradiction and non-existence proof is always subtle. All right, the language is context-free if it's generated by some context-free grammar, and we already said that 0 to the n, 1 to the n, 2 to the n is not context-free. Now, to prove that, there's a pumping theorem that's based on context-free grammars. It's a little bit more involved than this pumping theorem here for regular languages because it involves grammars, and it has 2 pumps, not 1. For extra credit, you can do a deeper dive into that, and you let me know how it works. It's not that much more complicated, but it's not worth half an hour of class time to describe yet another version of the pumping theorem. But there is one for context-free languages, and that can be used to show that 0 to the n, 1 to the n, 2 to the n is not context-free, because you have to have 2 pumps, and they're pumped up with the same exponent. So instead of just a v to the I, there's a v to the I and a w to the I, and the I must be the same in both. So now you have 2 simultaneous lockstep pumps in this version of the pumping theorem. It's a little more involved. It's for context-free grammars, context-free languages. And so you have to ask yourself, where are the 2 pumps in 0 to the n, 1 to the n, 2 to the n? If the first pumping is in the zeros, the second pump is only in the ones, ain't going to happen because there's not enough 2s to go around when you pump up zeros and ones. If 2 pumps are both in the zeros, ain't going to happen because there won't be enough ones. If 1 pump is in the zeros, 1 is in the 2s, again, ain't going to happen. So if 1 pump crosses the zeros, 1s, and 1 is only in the 2s, ain't going to happen because it'll be out of whack. So no pump can cross the 0-1 boundary or the 1-2 boundary. How many can see? That was more branches to this argument. How many can see what's going on? And you keep arguing where these 2 pumps can be. And the fact that there's 2 pumps is in the proof of the pumping argument for context-free grammars, which we're not going to explicate here in great detail, but for extra credit, look it up. Probably has its wiki page. It's mentioned in the book. It's mentioned elsewhere, and for extra credit, you can do it. Any other questions? All right, so we'll see you next time. And next time, we'll start talking about Turing machines. So we're out at the boundary of Turing machines now.